Okay, next up, last of the session, Thomas Fritz, in conjunction with Sebastian Mögel from University of Zurich.
Thank you. Okay, so I'm going to talk about leveraging biometric data to boost software developer productivity. And you've already heard a little bit about biometrics beforehand, but I'll continue on that line a little bit. Well, let's set out. Software is eating the world, as Mark Andreessen stated it in one of the Wall Street journals. And what he meant is basically that all major businesses, or most major businesses right now, their backbone is software, and there's more and more software coming into the world, and we have also a really, really high demand on more and more software being built all the time. Yet, at the same time, there's not enough software developers to really supply that demand. So as also pointed out by Felian, there's like 11 million software developers today, and there's, like, we're trying to recruit more and more people, but there's just never enough to really supply the demand of software that we have today. So the question is, how do we actually close this gap, or how do we get closer to closing this gap? One of the options is, as I said, like, we recruit more, we teach more students, we have more software developers in the end. The other thing is, we try to make every single software developer a little bit more productive. Trying to focus on each individual developer and make them more productive to really reach that, or close that gap in the end. Now, software developer, or researchers in software development have tried that for a long time. And what we mostly looked at so far, traditionally looking at, is looking at the output, the outcome that software developers are creating. So for example, the code or the work items and so on, and measuring these as a measure for productivity and trying to help software developers to improve their own productivity. So for example, there's research that focused on mining software repositories to understand where the defects in the code, and then to help software developers to lower the maintenance cost and overall increase their productivity. Now this is sort of like the traditional approach to increasing software developer productivity. And what the vision is that I want to talk about today is going over to the software developer and really focusing on the software developer more, trying to measure their productivity while they're doing their work and helping them in that case. Now, how do we measure software developer productivity? Well, in the past, there was, for example, the approach by Humphrey et al. On the personal software development process, where he tried to ask developers to write down exactly what they've been doing and sort of gather some process metrics from the software developer to actually, in the end, help them reflect on their productivity and increase their productivity. Now that's quite tedious, and then in 1999 there was, by et al., this framework set up, as you can see here, where there's already quite a few biometric sensors installed that people can use to then sort of empirically analyze the productivity of a software developer. But if you look at that picture, I guess you can imagine that it might be a little bit difficult to actually be productive. Just even thinking about getting cold feet all the time because you have that sensor on your small little toe. Fortunately, today, these sensors get smaller and smaller, and everybody is already wearing some of these sensors most likely. Like this is one of these sensors that already measures heart rate. So there's biometric features that are measured about myself all the time. And obviously we can take advantage of that and help software developers. The idea behind that is like what we call psychophysiology, or biometrics as I shortly abbreviated. And basically the idea here is that we have psychological aspects like states and processes that we can measure, or that are correlated to physiological features of a person. So for example, if somebody is very excited or stressed about giving a talk or giving a presentation up front here, I might start sweating more. And this sweating is obviously expressed, and I can measure that, for example, through the electrodermal activity. And psychology researchers have already established quite a few links between these two different sides. So they've looked at mental load and how it's related to, for example, the pupil size. That the pupil size increases, or that the blink rate slows down if I'm very focused on a task. Now, if you're porting that over to the software development domain, again, we have this idea of, we have the psychological aspects, the cognitive load, the mental effort, arousal and valence as well, and we have these biometric measures that we can actually grasp or gather from a software developer. Now, you can usually categorize it into approximately 5 different categories, like brain, skin, heart rate, breathing, and I forgot the last one. And I think that was, and the eye. And here's a couple of the measures. So for example, electrodermal activity, blood volume pulse, and EEG obviously, and then eye pupil size, and so on. Now, when the software developer is working, there's like tasks that they're working on, and the developer has also some experience that influence the cognitive load. So there's this 3 different types of, like 3 different loads. And there's the intrinsic, the extrinsic, and the germane load that influence the load, the cognitive load that the developer experiences. So how difficult the task is on the one side, how difficult it's expressed, or how the representation is, but also the experience and the expertise of the software developer that influences how difficult a task is being perceived and how high the cognitive load is. And that, on the other hand, as cognitive load theory also talks about, influences or affects how many, the difficulty or the errors that I'm creating, basically, the error rate of the developer. So how many errors I make in the code is related to how high my cognitive load was usually. Now, the question here is, if we can really measure software developers' cognitive and emotional states, what could we do with that? Also, for one of that is, if you can actually measure when it's difficult for a developer, so when does he experience, or she experiences difficulties going through the code, we might be able to tell, okay, this is a part of the code that should be refactored because it's causing difficulty to everybody. And we might actually be able to tell before the developer commits any mistakes or any errors to the repository, tell them, okay, maybe look over the code or refactor or prioritize the code reviews to avoid any mistakes being committed to the repository. At the same time, we might be able to measure the progress and the flow, or the focus of a developer. So for example, to give them or provide them a certain retrospection of their own work and tell them where could they improve and how could they be more productive in the end. And last but not least, something that was already mentioned is we could try and understand when a developer is particularly interruptible, when can we interrupt them if we have a question, and we can avoid these interruptions that lead to high error rate and that also lead to high cost because it takes a long time to resume the task in the end. Now, how do we do that? And I just give you a little bit of an overview of what we've done in our research, but there's already been quite a few, or there's been other approaches that have already used some sensors and tried similar things, but I'll just give you quickly some of the sensors that we used in our studies, and we can talk more about the other sensors obviously afterwards. So we, for example, used the neurosquare mindband, and you've seen it as well, that measures sort of the brain activity. And you can then separate them into alpha, beta, delta, gamma waves, and so on. And they have already been linked by psychology researchers to the mental load, the attention, the meditation, and so on that people experience on small tasks, not necessarily programming in this case. The other thing is the electrodermal activity, and that can be measured with a wristband here. And it has 2 components, the tonic and the phasic signal. And that can be measured, sort of the short-term thing, the surprise, and also the more long-term thing, the general state of arousal that people experience while they're working. And last but not least, here's the eye tracker that we can use. And obviously that can be used for multiple things to measure. One of the things is you can know exactly where people are looking at, but at the same time you also know something about the pupil dilation, how big the pupil is, and you can tell also something about the blink rate, obviously. That again tells you something about the cognitive load that people experience at the same time. Now, how does a normal study setup look like in our case? So you have the developer as from one of our field studies where a developer is actually sitting at his normal desk, having his normal screens and laptops around. The only things that were different is that he actually had to wear the neurosquare mindband and also that wristband that captured the biometric data. And at the same time, we also installed a small little tablet on the side that interrupted him from time to time so that we can actually assess and gather some self-reports from the software developer. Now, if you're looking at it from the other perspective, and just to give you an idea how good eye tracking is today, for example, here's the software developer sitting there, he's talking out loud, here's the mindband on there, and at the same time the eye tracker is running, so you know exactly what they're looking at. And also the size of the red dot is basically showing how long he focuses on a particular part in the code. and how fast he switches between the code as well, and where he's reading along as well. So by tracking that and tracking the biometrics at the same time, we can sort of tell what's going on, a lot more what's going on in the developer and what is he doing. Now, the general approach then goes on to say we gather all this data, so they have those sensors on, then we gather data from these 3 different sensors, and here's just like screenshots of the data we go. And then there's quite a bit of a data pipeline, because so you record the data, and then you have to do a lot of data cleaning, because there's a lot of noise in the data as well, because it's biometric data. And then you have to use possibly a sliding time window to select certain time windows of data that you're interested in. You have to extract the features that you're interested in. And then in the end, what you usually do is you use or train a machine learning classifier and use it to predict certain states or things that you're interested in. In this case, we used it, for example, for perceived difficulty that people experience while they're working on tasks or while they're working on code, and also on the interruptibility. So going back to one of these aspects that I talked about, sensing task difficulty, how could I actually do that? So there have already been studies by, for example, Chris Panin that has used sub-vocal utterances, for example, to measure how difficult it might be. And I'm going to just talk about the one that we have done before, and that was in conjunction with Andy Wegel, or together with Andy Wegel and Sarah Kiengett-Elliott, and also Manuela Züger. And here the question was, can we actually use these biometric sensors to help software, to support software developers? In particular, can we use them to predict whether a task is perceived as difficult or easy, and in particular small programming tasks or code comprehension tasks? And then can we also, like, what kind of combination of sensors do we need? Like, can we use very few sensors to actually predict that? Or do we need a big set of sensors? And also, how long is the time window that we need to actually make these predictions? So can we, for example, do it in real time? Can we do it instantaneously? And what we did here is we had experimental design where we had 15 professional developers that all had a certain experience, programming experience already. We designed 8 tasks, and I'll talk a little bit more in a second about those. These tasks were from 1 to 8 minutes long, like that's how long the developers took to usually finish them. And then we also had 3 biometric sensors on them. We did a lab study in this case, so developers or the professional developers would come in. They would sit in front of the monitor. There would be an in front of the computer. There would be an eye tracker. They would have to put on the EDA and also the Neosquare mindband. And so we would track their biometric data. And then at the end, after each single task, and also at the end of all of the tasks, we asked them to rate these tasks, to rank them, and also to fill out the NASA TLX load so that we got some measures on the difficulty of each particular task. Now, when you look at the task itself, we had 2 different types of tasks. One of them was asking them to whether or not 2 rectangles that were drawn are overlapping, and the other one was drawing different shapes on the screen, on the output, and basically we asked them in which order are these shapes being drawn on the output. And we chose these tasks and designed these tasks in a way that we also switched a couple of things such as the variable names, or for example the loops that we had in there. We added nested operators and also randomly assigned randomly ordered field assignments. And the reason why we did this is because we wanted to stress different sort of cognitive abilities that developers have. So we wanted to stress their working memory, we wanted to stress their math and logic skills that they have to apply to actually solve these tasks. And obviously we made some tasks a lot easier than other tasks, just so we can see if there's actually a difference that we can note in the biometric data that we gather. Here's just one of the examples that you can see. It's like, okay, so on the left side, you have a rectangle drawn on the top and in the bottom, and then on the right side we have a similar 2 rectangles drawn as well. But here you see that the order was randomly assigned, so it makes it a lot more difficult for the developer to keep track of, okay, are these rectangles actually overlapping or not? Because you first have to sort of order them in your head, put them together, and then look at the overlap or not. Now in the end, for this experiment, we had 15 developers, and each one was solving 8 tasks. So in the total, we had 120 tasks, and we randomly assigned the order of the tasks to the developers to avoid any learning or to counterbalance any learning effect that people have. Now the interesting thing is that you have to do when you deal with biometric data is you sort of have to gather a baseline. So each one of them had, between each task, they had to look at a 2-minute YouTube video. One of the things that happens is that in the first minute, sort of they slow down, the biometric features usually drop to a certain baseline, and in the second minute you can use that as a baseline that you use to, for the features afterwards to calculate them in a normalized way. In machine learning, so first of all we gathered different biometric data, and here just some of the examples. So we used the eye tracking, the EDA and the EEG, and you can see here the different features. I've talked a little bit about them before, and so we have the alpha and the beta and the gamma delta and theta waves. They're very well established. There's always certain indices, such as the task engagement index, and in the end that's sort of like beta divided by alpha plus theta, that psychology researchers have already come up with to say, okay, this one is related, or can be correlated to the task engagement that people experience, and obviously other things like the number of fixations or the number of saccades and so on. Then we do the naive Bayes machine learning in this case. You can see here, for example, we trained it by task, but we also did by participant to see if there's a which one works best and how does it work, and can we actually achieve any accuracy or any precision and recall with these sensors. And in the end we also switched up the time windows that we have, because we wanted to see how much of the biometric data do we actually need before we can make an accurate prediction of how good, if that task is difficult or easy, because that really allows us to see whether or not we can use it in the field and actually help developers while they're working on the code. Now here's some of the initial results, and as I said, that was one of the first studies where we went into more depth with software developers. So I mean, the results aren't perfect, but they're still pretty good to see that we can achieve a fairly reasonable precision and recall. And what we can see here as well is that the combination of the EI, the EDA, and the EEG is definitely the highest, or achieves the highest results, but at the same time they're not so far off from the other results as well. And so obviously that's promising for the future, because we might not always be able to sit somebody in front of the eye tracker or have enough eye trackers for them and have them wear these headbands at the same time. And then we also looked at the time windows. And the time windows you can see here is like, even with 10 seconds of a biometric data, you can make fairly good predictions. That means that really after a very short amount of time, we can tell, okay, this task is difficult or this task is easy, and then possibly, well, not interfere, but basically support the developers on the fly. So coming back to the questions that I talked about, here's, can we use biometric sensing to predict the perceived difficulty? And we were able to do so. And also we can do that particularly well by task with a 10-second time window, and also with a combination of all 3 sensors to get the best results. Now going back to the measuring developer cognitive and emotional states, and how can we help support software developers. So the first thing I talked about is the sensing, task, and code difficulty. We've also conducted a field studies where people had actually were wearing these sensors for 2 weeks, and then we tried to find code defects or like quality concerns that people mentioned in code reviews afterwards, and Sebastian will present their work at ICSI, and we've also found positive results or encouraging results in this study. Another one is sort of, we looked at, can we measure the emotion and progress, and we were also able to distinguish between negative and positive emotions, and also high and low progress with a high accuracy. And then we also looked at, can we go and sense the interruptibility of any software developers while they're working, and there we did a combination of a lab and a field study. Again, and obviously in the lab study works a lot better because there's a lot less noise, but even in the field study where people have a lot of noise, a lot of, from the outside, different changes in lights and so on, it is possible to do so. So there's some of the opportunities and challenges, and I won't go into much detail here, into much depth in here, but there's definitely, what we've seen is there's quite a bit of potential here that we can use these sensors to predict certain things about the software developer, about his cognitive, about her cognitive, and about her emotional states. And the great thing is that there's more and more of these smart devices that already gather some biometric data about the software developer, and they're becoming more pervasive all the time. So people might be already wearing Apple Watches, and they collect the heart rate underneath, as well as the Microsoft band, for example. At the same time, there's obviously quite a few concerns, such as the privacy, as Shane already pointed out, And there's limitations for the sensors. So for example, one company actually went under, and we still have the sensors, but we can't use them anymore because the company doesn't exist. And obviously it will be better over time with more and more sensors coming out. So just to sum up, the idea here is, or the vision for me, for the biometric sensing, is that we want to make developers more productive, and we also want to make them happier in the end. So far we've usually looked at what have they done. So what is the output, what are the artifacts that people are producing, and trying to measure them, trying to help them with that. What we want to do is we want to go into understanding how they're doing their work, what's going on, what are their cognitive, what are their emotional states, and the processes that they're going through. And then we can use the biometric sensing to really support software developers. And we can use that to support them, for example, by preventing interruptions that are expensive, or by avoiding that they actually submit any code that has bugs to the repository. And so just to point that out, obviously in the end that wasn't just my work, but there was a lot of work that I did with my PhD students and also with Andy Biggle from Microsoft Research, and there are other collaborators that helped me on that. Thanks.
Yeah, thanks for your great talk. Thanks for your great talk. My question is about how to analyze this kind of data, because I understand how we can easily do within subject analysis, but then what about between subject analysis? And I will explain you the problem. You know, already comparing between subjects productivities can be challenging, but when it comes to comparing the heart rate, the sweat, and so on, you know, people can be very different, because, for instance, I know my heart rate is easily going up to 200. Oops, now this is on YouTube, but anyway. So
that's a very good point. So biometric data is very individual, that's true. There's a high fluctuation of how well it works for each individual developer. So for some developers, and we noticed that in some of the studies, it works really, really well, and for others it doesn't work really well, or it's other features that work well. So it just might differ in the features. The good thing is you use certain baselines usually to measure, to normalize the data by individual to a certain extent, like looking at the YouTube video for 2 minutes, and then we can see, okay, your resting heart rate is a lot higher than somebody else's resting heart rate, and that helps. But we also train for both sides. So for example, we looked at, okay, can I train on 14 individuals and then predict for the 15th individual? That is possible, but the accuracy is a lot lower in that case, obviously. And the question is it just because we might need more data? But I think it will always be a lot better when we train on each individual, and it might be worth the little bit of training in the beginning that you
have. Good talk. So, as in any prediction, there's going to be false positives and false negatives. Have you thought of what the costs of those would be? Like, if you're making the wrong recommendation to the developer, how is that going to affect, and is it going to go into a downward spiral?
Absolutely. So I mean, we've thought about it. We haven't come up with good approaches for that one. It depends on what kind of support you want to build. So the one thing is, for example, interrupt them. So when we notice that, we can tell when developers are very frustrated, for example. And in that case, it might be helpful to tell them, maybe talk to a coworker because he can help you in that one. The other thing is, we might tell them, okay, maybe take a break and go for a walk. That might be very annoying. It might be very annoying whether or not we hit the frustration or not. But basically, figuring that out is something that we have to do in the future and really understanding when it helps. For the code concerns, for example, when we noticed, okay, when we were able to predict sort of like where are bugs being created, those are very, very few things. And if we can do it at the right time, like say, okay, instead of looking at, so just prioritizing code reviews afterwards, it might be very non-invasive and help software developers in the end.
So I was wondering, you mentioned at some point you had to do filtering because data is some fluctuation and noise. Also, you focused on relatively limited tasks, I guess, to also keep the noise low. Now, what do you think about the accuracy of these sensors for longer tasks, like monitoring for longer time? Do you think filtering techniques are advanced enough?
So it's a really good question. So we have tried to vary the studies quite a bit. Like in the beginning, we started out with very, very restricted lab studies with very, very short tasks. And in this case, it works fairly well with the filtering techniques that you have and so on. And then when we've been out in the field, obviously, you have less sensors actually. and you have a lot more noise. So even like the change in the light, like if you switch on the light bulbs or so, and that affects the sensors to a certain extent, or the data that's being gathered from the person. And so far we've always been able to get good enough results. Like they're definitely not as good. So for example, when we looked at interruptibility in the field versus in the lab, we can differentiate between 5 different states of interruptibility in the lab with a certain accuracy. In the field, 5 states is just not possible anymore. 2 states is okay. 5 states you're not good anyway, like any better than just randomly doing that. We've also done a 2-week experiments where we're wearing these sensors, and it was still good enough. It's not like the highest accuracy for sure, and I think that'll improve a lot in the future, and better techniques will actually help with that for sure.
Thank you, Thomas, for the interesting talk. I was wondering more generic question. Was there any resistance from the developers to wear these wearables? I know some of us do it for free, for fun, but especially if you then ask developers to be monitored, what did you say? Did you do a survey, for instance?
So I must say that the hardest thing is to actually recruit participants for these studies. Like, it's a really good point. Like, it was really tough to get anybody to participate in that. For the shorter ones, like wearing them for an hour, 2 hours, everybody is okay with that. And if you send your students there, they're usually nice, they bring chocolate, especially Swiss chocolate works really, really well, and they're happy to participate. For the longer study, when we had this for 2 weeks, I was actually sitting in a company for a month or two beforehand to, you go to the coffee breaks, you chat with them, and you slowly smooth them into the idea of wearing these sensors, because that is very invasive. And even then, you bring a lot of chocolate, and even then you bring croissants every morning and so on. So it is not easy to get them in the first place. I do think that'll change in the future when everybody's wearing a Microsoft band or an Apple Watch already, and the sensors inside of these devices get better. But so far it's definitely a big hassle, and sometimes, like, that's why sometimes the numbers are very small actually.
Thank you for the talk. You mentioned in the first introduction that it's important for organizations to actually measure how developers are doing in their work. So from management perspectives, do you think that biometrics data are trustworthy and actually reflecting the work that the developers are doing and can be adopted in future? Thank you.
That's a good question. So there's like multiple questions in there almost. Like the one thing is sort of like, I don't think that we're at this point where we will give it to the manager. And for multiple reasons. One of them is the privacy concern, because we don't know what can we do. And I'll talk about that later on in the roundtable a little bit more. The other thing is it trustworthy? Do I believe in the data? That again depends on what am I going to present. So I can tell you with high accuracy, okay, that's your blood volume pulse. How much is that correlated to the flow that you had in the day? And then if I take that away and say, okay, that's your productivity, I think there needs to be a lot of research being done that we have the confidence to say, okay, this is the right value to abstract and this is the right value to present to the people. But I do think that biometric sensors by itself are harder to manipulate than anything else. Like to a certain extent, or at least over a long time. Like maybe in an hour you can say, okay, no, I just run up the stairs so that he thinks that I was really stressed in my work or something. But usually you won't do that all the time. So I think that they can be fairly accurate at some point in the future where we have the right means to abstract them to the values that we're interested in.
Yeah. So you can imagine this same story for any general worker, someone that works, does anything else apart from developers. So what kind of are the differences and similarities in these two scenarios?
So what is the difference and similarities between a general information or knowledge worker and a software developer? Or?
Yeah, so in the sense of monitoring the productivity, so what's, why are you focusing on software engineering, for example, and not
anybody else? So I guess I started out in software development and I always wanted to help software developers to become more productive and happy in the end. So that's where my interest in helping software developers come from. There's a difference obviously in the artifacts that we deal with and the work that we do. First of all, because code is just very different to, not different to Excel sheets apparently, but it is different to other things, and we can track that very well as well with software developers. I do hope that in the future at some point we can actually use these insights and port them to other domains as well, and then we can use them in these other domains to support a general knowledge work as well.
And then last question from the past. Apart from having contributed to the Swiss chocolate industry, which is very nice, is this software engineering?
Why would it not be?
He didn't ask you that.
So for me, it's always a question is like, how do I help software developers to become more productive? And I think I can look at that from a point of view where I say, okay, I go in the IDE and I help them use those tools in the IDE more productively. Or I can look at the bigger picture and look at how much time do actually developers spend in the IDE, and then I see that's most likely 20 or 30% of their time. And then I focus on the bigger picture and trying to make them more productive in the whole time. So if interruptions, for example, as studies have shown, increase the error rate, or increase, for example, if I have 2 interruptions that can cause an hour of delay in a day, that's like a lot of productivity is being lost. If I can actually improve that one, I think I can help software developers tremendously becoming more productive as well. And it might just be at a different level. But I still think it's software development. Thanks.
So let's thank Thomas.